So welcome everyone to our second talk of the seminar series between 2024 and 2025 of our technical committee on model-based optimization for robotics. Today our speaker is Jan Abraham, and before we start the talk, I just want to remind everyone that the session is recorded, including the question session. So if you don't feel comfortable with asking questions in person, you can also post them in the chat, and we can get our speaker to answer them. The session then will be posted on our YouTube channel, and you can find the links afterwards on our website. I will also take the occasion to remind everyone that our Best Paper Award of this year deadline is tomorrow for submitting your papers. So if you are considering you have had a really good paper from last year, self-nominations are also more than welcome. And please submit your nominations by tomorrow. I will drop the link after the talk has started in the chat. Yeah, so let me introduce then our speaker today, Jan Abraham, who is an assistant professor, mechanical engineering, material science at Yale. And today, Jan will give us the talk titled Optimality and Robustness in Robotic Exploration. Looking forward to the talk, and the floor is yours.
All right, thank you so much. Thank you for the invitation. So today I'm going to talk about what my group has been thinking about for the last couple of years, which is thinking about really what does it mean for a robot to be optimal and robust in the way it explores and really the way it collects data, right? Because we deploy robots every day, and the first thing we have to think about is, well, hey, it has to adapt to its environment. So data collection and exploration are incredibly important. So ensuring that that is both optimal and robust under any circumstances is incredibly ideal. So the way I've sort of outlined this talk is first I'm going to dive into the motivation, why we're doing this, what's been done, et cetera. And then I'll talk about the technique that we've been using in my group and developing, which is called ergodic coverage. I'll talk about what it means to establish a notion of ergodicity. And I'll talk about how do we actually create what we call an ergodic controller out of this ergodic statement. And then how do we get certain properties? So for instance, time optimality, robustness, and a notion of generalization exploration, and how that actually is going to help us out and what my group is thinking about in terms of robot learning, which is what we're exploring currently. Okay, so the motivation. Oh, is there someone in the chat? Oh, good. Okay, so motivation of our work, robotic exploration. We see this everywhere. We have robots being deployed in subterranean environments, and they have to go map their tunnels. We have robots going out in rubble and in uncertain environments to help people in search and rescue applications in order to find signs of life. We also have robots that are doing some sort of environmental monitoring, which requires them to have a bit of exploration, both short and long term, in order to understand long-term trends and short-term trends in the environment to help us better understand the impact of human activity. And last, we also have exploration in space and ocean. We humans cannot visit some of these places, at least safely. So robots go in our stead as a means to collect data and report back, tell us our findings, and be that investigative person in the field. And so each and one of these applications has a notion of required exploration. The other ones that Mike was also looking into is robot learning. So how exactly can we use robot exploration to help robot understand and explore its own dynamics, its own interactions and environment, and then learn from those interactions. All right, so what exactly is the problem? Well, it's exploration. What it means in layman terms, the way we looked at it is getting a robot to visit places of interest and collect data. There are a couple questions that arise when you think about this problem in those terms. First is, what is actually the form of data? How do we actually determine what is the place of interest that we want a robot to go towards? How does actually that robot goes from A to B? And what's the role of the sensor? How does that sensor impact the robot's navigation as well as its exploration? And the things my group started caring about a lot more is, well, how do we actually guarantee that the robot visits every single place, right? Going to certain places of interest is good, but what if the information is not there? How do we then adapt to that very quickly? In particular, how fast does exploration take? I could send my robot to go mapping, but do I have a good idea that it'll first give me a course map and then refine the map, or will that take forever? Can I put a number to it? And last, so how does that coverage or exploration problem change across different domains? So I might be looking at a map or a mapping problem, but it might change when I move towards, say, exploring my own state space or my C space. The exploration will change. Question: how does it change, and can we actually make some generalization statements about that? So my group is not the first to explore these problems. This sort of started back in the 80s with this idea of active perception. And then later on, we started thinking of this more for coverage problems, specifically, doing coverage for inspection on objects. And then more recently, we had quite a bit of work where we started thinking of more hierarchical methods to do exploration and mapping, where we discretize your space in different fidelities, so high and low fidelity, and then we explore to that. And then more recently, we've had work on information-based planning, specifically by Hollinger et al., where they were looking at more information theoretic ways, so sensor-driven ways to establish active planning and exploration in order to do things like underwater inspection. And then more recently, some good work out of Vijay Kumar's group is doing active perception via robust exploration. So there's a lot of work in this area, but the thing that sort of drew the attention of my group was this question of whether we can actually generalize exploration, not specific to the sensor, its application space, or the robot itself, or what is the information, but really in more unifying formulation that's really independent of all these concepts. The idea is we want to understand the problem exploration and then add in things like the sensor, the dynamics, what does it mean to have information and information gain as sort of an add-on rather than being the thing we set up in the beginning. So this goes back into why we talk about ergodic coverage. And when we do that is through ergodic coverage. Okay, so what exactly is ergodic coverage? First, I'm going to talk about ergodicity as a statement. Okay, so what is ergodicity and why do we use it? Well, we define ergodicity as establishing what we call an ergodic property, which says that a dynamical system is said to be ergodic. So we call dynamic system some robot, for instance, or a process is ergodic if on average that trajectory or that dynamical system is spending time in regions proportional to the utility of exploring that region. Okay, so what that means is we're making this specific statement where a robot visits on average is proportional to how useful it is to be in that place. And so the way we establish this is via this statement, which says that, hey, some measure along that trajectory has to eventually equal the spatial average distributed over the space. And for t going to infinity, we say that ergodic trajectories actually provide a notion of guaranteed coverage. We will actually cover every space. However, it requires t going to infinity. So we have the statement. However, that assumes that our dynamical system is already ergodic. Unfortunately, we don't actually have that. So we have to have robots don't actually naturally come out with this ergodic property. So we have to actually have a way to measure ergodicity. So the way we do that is we define an ergodic metric that allows us to compute the distances or a trajectory's distance to being ergodic with respect to some notion of information. This is independent of the problem. We just give whatever information or some uncertainty value is to a metric, and then we say, okay, be ergodic with respect to this. So typically the way we did it in the past is using the Fourier transform. So we would say, okay, I'm going to take that ergodic statement. I'm going to be sub-ergodic. What that means is I'm going to only look at a finite time horizon, so some TF. And I'm going to say, okay, measure the distance between that, the trajectory that we're generating. And we're going to assume our robot's trajectory is a delta function, which represents as a delta function. It's nice because we actually get a nice clean representation of it in the Fourier space. And we compare the Fourier modes of that time. This is what we're calling the time average trajectory statistic. That's where it's generating and comparing the modes of where it's visiting or on average to where it should be spending the most time. So what you get as a result is something like you see on the top right here, or in the case of a uniform distribution that you're kind of covering in space, you're going to get something that looks exactly like a lawnmower pattern. And the thing to note here is this kind of looks like a normal L2 model-based control cost, but in fact, it's not. There's integral of time on the inside. You have this FK, which is a Fourier basis function, and you have a square on the outside. And this is for a single basis mode. So what you're doing is you're really taking a spectral decomposition of your trajectory, comparing it to that spectral mode where you would like to spend time based off your information, and then taking an L2 norm on that. And so this is actually not so necessarily as straightforward. So something you can just throw into ILQR. It's a bit more complicated. So how do we exactly go about getting trajectories that are ergodic, which have this kind of behavior where you're actually spending time proportional to areas with probability, whatever is distributed there? The way you do that is actually, turns out the Fourier transform is differentiable. So you could just throw that into any nonlinear program where the ergodic metric E here takes in both the full trajectory and here this phi term, which we're going to call the information measure or some information distribution. So it could be a uniform number, so one that's distributed over this, equally probable to visit everywhere, or it could be something a bit more biased, like this bimodal distribution. And so what you're seeing on the bottom right here is an example of a trajectory solution that is ergodic. So on the left is sort of the specification. You have these bimodal peaks to say, hey, I would like my robot to visit these places with equal probability. And then the thing you're optimizing is on the right-hand side, where this is the trajectory of the robot. If you're looking at in the background, it's the time average trajectory statistics. So this is where does the robot spend time on average? Okay. And so you can also put in a bunch of other constraints, so control costs, state, control constraints, dynamic constraints, et cetera. So it's very amenable to this trajectory optimization formulation. So what are kind of the advantages of ergodic control? One thing is given a compact domain, so something that's bounded, in this case square, you can actually achieve ergodic dynamics. So you get, in the long time horizon case, where you have a uniform distribution, you get a lawnmower pattern. You really can't do this with an information maximization method. These are exactly what you get if you were to do some Balstrophodon kind of coverage patterns. So what your Roomba is really doing. And we get this for free in the continuous space. And that's sort of what's exciting here, is that we're able to get those kinds of patterns where if we don't know anything, we'll search everywhere. And in the cases where we know something, search specifically in those areas. However, if we increase the time horizon, you would start filling in the gaps everywhere else. Downside, though, is it is a nonlinear, non-convex optimization problem. But here's the advantage. It's actually has a lot of these very good local minima. What that means is I can explore this bimodal distribution and collect data in this direction, or I can do it counterclockwise, where the robot actually goes the other direction, and I would get exactly the same amount of ergodicity in terms of the metric, and it would be the same amount of information gathering. That's what's exciting. We can actually determine multiple different ways to actually go about exploring a single domain. The other advantages is that first is that it's independent of the dynamics, the domain, the sensor, and what we're defining as information. This is just coming in as an argument, and we don't even need to have the exact explicit function. We just need to be able to sample from what we define as information, which is pretty exciting. It's also non-myopic. So what I mean by that is that we can actually formulate this over long planning horizons. These trajectories are solved at once. So you get derivatives over the whole trajectory, as opposed to being some sequential decision program. We have to decide, if I go at this point, where do I go next? And the impact of that. We're looking at the trajectory as a whole. So it's in a sense a global optimization formulation. And the thing that I find interesting and exciting is that, in fact, this problem reduces down to information maximization. When you have a very short time horizon, you will go to just the peak of one or the other mode. If you reduce the time horizon, in fact, that's not necessarily true. You will still explore all the other information modes if you have a short time horizon. But if you have a long time horizon, the problem becomes a bit more like an information gathering problem. You won't just go to the peaks, you actually go everywhere else and explore all the little nook and crannies. And so some applications, which I won't be able to talk about too much in detail, that we have done in my group. One is we use this to actually enable a Mars Curiosity rover to do exploration for sedimentary rocks on the simulated platform. So we actually hooked up a image classifier to this problem, and No, we didn't even have to define a necessarily information distribution. This is something we would just sample. You don't even need derivative information, which is actually very exciting. So all the information just comes from what you define as information, how you sample that. And so we actually get to define both the control, or we get to establish the control problem and the information and the sensing problem as independent of one another. The other thing is that, yeah, your sensor constraints are actually not even explicitly defined. They actually get brought into the way we define information. We could also do this the other application of my group, where we looked at doing exploitation, but in a sense that is safe. So we've integrated ergodic control with safety filters, and we were able to, for instance, go about and sample these for these three high information peaks while avoiding obstacles in the environment. And the flexibility of the metric actually allows us to really consider ensuring that safety is established without impeding on the coverage or the collection, the exploration performance. We're also able to do this on a multi-agent system, which I won't talk about a lot today. So what's cool here is that this is also being derived, these trajectories being optimized through the ergodic metric. And what's really exciting is all these reroutings that you're seeing happen naturally. This is something that we did not explicitly define in the optimization, and the ergodic metric and sort of that trajectory optimization formulation naturally came up with these kinds of solutions, which is really exciting. And this is for uniform coverage in some cluttered environment. So these are the applications that my group is working on. What I'm going to talk about today is sort of what it means to be optimal in certain regards and robust that my group is recently thinking about. So the first thing we're going to talk about is time optimal exploration. So how fast can a robot explore, right? So we were really interested in where we asked, okay, well, what is, if I get a robot, a Roomba, and I want to clean my room and I know roughly the bounds, what's the minimum time it would take to clean that room? Or in this case, explore the area, right? It's going to be useful in mapping. It's going to be useful for my Roomba. I like to know, hey, what's the best case and the worst case time? If I want it to get a very coarse map, can you please come back and tell me how long it's going to take? We ask, how can we actually compute this? So one thing we can note is that the actual ergodic metric that we defined is based on an average time a trajectory visits an area. Okay, so note here, there's this 1/t. Now, that's really important. Okay, the other thing that's really important is that the metric is being calculated using the Fourier spectral composition. In fact, most of the time, we're going to be looking at most of the ergodic metrics are some notion of spectral decomposition. What that means is that we're going to actually promote coverage and exploration evenly across spectral modes. Okay, and that's really important because if I want to explore space very quickly, but I have some area over far away that has some high information, I like to still visit that, especially if it has a lot of information compared to somewhere closer to me. And so having this spectral approach actually lets you reason about sort of far away places and time as well. And so again, note that the ergodic metric is inversely proportional time. So in a sense, we could just stick the ergodic metric into a minimum time problem and then say, okay, minimize time. The issue though is that it's actually an ill-posed problem. Note that time has to go to infinity for this ergodicity statement to be established. So if you looked at the metric, a solution actually is that t has to go to infinity, which means we'll have infinite time. And that's not necessarily what we want. So what we did instead is we said, okay, look, that metric actually can instead act as a constraint equation. We can put into it as a constraint, not as the main objective, and then put an upper bound on it. We can say, look, be ergodic up to a point. And what that does is it actually provides an upper bound or a lower bound on, provides an upper bound on coverage, which is exactly what we want. We want to say, hey, give me some minimum level of coverage so that time can be brought up to that point. We don't want infinite time, but we want to upper bound time. So we did this was to rewrite the problem as a minimum time problem, where we use the ergodic metric as a constraint. This is done by my two students, Ethan Dong and Henry Berger. So the idea is we are going to minimize time, subject to dynamic equality and inequality constraints. And then we're going to add this minimum ergodic coverage constraint with respect to some utility measure. We're going to have some phi that we define ahead of time, and we're saying, okay, get some upper bound in there. But it turns out that upper bound actually has a really interesting meaning where it actually is related to how much or some percentage of how much information you want to draw out or collect from your original information distribution or information measure, which is kind of exciting. So we have some connection between that upper bound and how much that robot is exploring. And then the way we actually compute this is, well, first we prove that it has some locally optimal, it is a solvable problem. Um, the way we solved it is using direct transcription. So we converted the problem and transcribed it into some n knot points, and we then solved it via the KKT conditions. So this is the discretized version of the problem, where what we did instead is we say dt is solved via whatever the final time that we're trying to optimize is. So your step size now encoded through these n knot points. So that's a parameter we pick ahead of time. You transcribe your trajectory over those knot points, where now dt determines how big of a step you're going to take. And then you compute a discrete time ergodic metric, which is very similar. You just replace the integral with the sum. So what does that give you when you optimize this? Well, we actually get a huge diversity of coverage behavior and exploration behavior. So on the left here, what you're seeing is a uniform coverage problem over a cluttered environment. And what we're doing is we're reducing that upper bound closer and closer to zero. And as we do that, what you're seeing is exactly what we expected, which is that the robot wants to spend, or the trajectory we're optimizing spends way more time everywhere and spreads it out as much as possible throughout the space. Whereas if we cut it very high, it jumps to very quickly zoom through the space, collect data, and then call it a day. And so obviously, as we keep reducing the upper bound, time is going to start increasing quite rapidly. So this is cool. So we get to have a bit of a flexibility in how our robots go about exploring a place, and we have a time associated with it as well. We can also bias the search in some meaningful way. Say I know ahead of time, I like my robot to spend time in these areas. For instance, it could be a place where I have, oh, there's signs of life there. I like my robot to go quickly collect data. Well, I can actually optimize that and include that into our optimization, where now you see this is where the spectral part comes in. We are encouraging a robot to first quickly go through all the places of interest. And then as we reduce that upper bound, we get more and more thorough coverage, which is exactly what we wanted, right? Collect more data in those areas of interest because they might actually yield something more interesting that we don't know of. So we tried this on a bunch of some experiments. This is a very thorough search. We use a closer upper bound or tighter upper bound, and we were able to get about 32 seconds. So that was a number, and then with the constraints, we actually get pretty good correspondence with the experiments. So there's a robot doing this coarse kind of coverage over the space, or sorry, excuse me, thorough coverage. And then here's an example of a coarse search where when we optimize it, we said, okay, like go as fast as possible. And so the direct optimization did so accordingly. So the other neat application of this sort of minimum time approach is that we actually write this as a receding horizon controller. And what's interesting about that is if we write as a receding horizon controller, having a final planning time that's changing doesn't make much sense. But what it does is it actually allows us to adapt sampling times and sampling fidelity. So that means that there's features that maybe require a bit more sampling and they're, for instance, more higher frequency. We would actually adapt our planning scheme so that we would take advantage of that. And so what you're seeing on the left here is some notion of information, we call the EID. And the middle is a belief of where an object is, where we're locating. We have a low signal to noise sensor that we're using here. And the robot's able to actually readapt its planning horizon and its sampling so that it can actually very quickly converge onto where the object is or where the target is. The other thing to note is that when we compared it across different versions of ergodic search, one of the advantages we found is that just with a time optimal upper bound using this receding approach, we're able to consistently localize the target pretty quickly and reliably. Whereas if we try to have a fixed time horizon, you would get very disparate behaviors or much slower behavior because we didn't have the ability to sample accordingly to the information and its features. So this is sort of another nice application of time alters, and we were able to actually provide these bounds, which is incredibly exciting. Okay, we're going to talk about robust exploration. Actually, curiosity, what's the final time?
It's at 10 a.m. So
10
that's
a.m. Okay,
including technically questions. So yeah.
that's what's confirming. Okay, all right, thanks.
All right.
Okay, then in which case, we're going to talk about robust exploration, but I'm going to zip through the first part a little bit quickly. Um, so we just talked about time optimal exploration, which just says that what's the final time to explore? We got numbers. Good. Now we're interested in, well, can exploration be robust? And we approach this via two different ways. Um, the first is that we asked the question, whether we can guarantee coverage fidelity under any dynamic disturbances. The idea being that um, when we deploy our robots, if let's say, we did just some path following and some Bostrophenol pattern, and the robot had some disturbances and it was pushed out of the way, there would be no notion of coverage at that point, right? It got pushed away, it didn't actually collect any data. We wanted to encode that and say, well, no, I want to continue, I want the robot to persist and try to, as much as possible, provide a sufficient level of coverage so that we know that enough data was collected. And so the way we thought of this problem initially is as a reachability problem, achieving levels of ergodicity. So I'm going to kind of brush this a little bit quickly. The idea is we just want to find a controller that minimizes some performance metric, in this case, levels of ergodicity, so some upper bound of ergodicity, such subject to worst case disturbances. And the way we did that is via Hamilton-Jacobi-Isaacs reachability analysis. One of the caveats is there's a specific form that the HGI problem needs to be placed in. And the ergodic metric, unfortunately, does not have this form. In fact, it takes a whole trajectory. And so one of the things we had to do is what my student did. We just presented this at Wafer in Chicago this past year. Is he said, well, it turns out you can actually redefine the ergodic metric with these we're calling extended ergodic states. Okay. And the idea is that we can rewrite the ergodic metric as not just this function that takes in a full trajectory, but instead as a terminal time condition subject to these additional, we're calling ergodic states, which are, think of this as a continuous visitation tracking. So like some occupancy map, but this is defined in the continuous space. And so the dimensionality of this is the number of basis functions that we're using. And so when we did that, we can actually write down, or we're going to call the extended ergodic control problem with disturbances. And then we applied reachability analysis to it, specifically deep reach, in order to get a controller that allowed the robot to persistently get a certain level of coverage and exploration. So this is, we want the robot to cover with respect to this binary distribution. And what you're seeing in gray is where the robot's actually spending time. And so here you can see that the value function, which is also controlling the controller or directing the controller, is actually pushing the robot towards areas where it's like, hey, you haven't visited here enough. You should probably go there to at least achieve some level of coverage. So my student did some experiments with this, which is really exciting. But sort of the issue here, as you've taken notice, is that we're really limited to very low dimensional problems. And this is sort of the problem with this approach, is that, well, the dimensionality of the problem actually exploded pretty quickly. It was, in fact, it would be n to the power of k, or k to the power, so k to the power n, k being the number of basis functions. So there's this exponential explosion because of these extended ergodic states. So they made HCI reachability a bit intractable for us because these methods tend to scale very poorly in terms of high dimensional spaces. So the other approach that we came up with was to think of robustness and expression via variational inference. This is work done by my colleagues, Derek Lee, PhD student Cameron Larch, and Fabio Ramos at NVIDIA. So the idea is that we said, okay, we know that the ergodic metric has these multiplicity of solutions. Do we use that in some meaningful way to gain robustness? In particular, we were asking, is it possible to reason about maybe several different ways to explore a space as a way of saying planning for the worst and hoping for the best? Okay, what we're seeing here are sort of two examples. What we don't want is where we sort of just randomize trajectories and then all those trajectories collapse into sort of exactly the same behavior. What we want is tons of diversity and tons of backup plans. So in case something were to happen, my robot can easily switch between strategies. So the way we did this is we actually treated the problem of ergodic coverage as a inference problem. We said, okay, we're going to think of the ergodic metric and add it as a likelihood model. Okay, and we're going to use something called Stein variational inference to solve an approximate posterior. This is sort of a method of approximate inference where we don't necessarily have to solve the exact posterior, but we instead solve samples. And so these samples are going to be trajectory samples. They're going to be solutions which govern different kinds of exploration strategies. So this is sort of an example of what that looks like below for navigating this maze. So the way we actually implemented this was we said, okay, let's take the ergodic metric, put it into this likelihood model form, okay, add in a prior so that we can ensure that these trajectories are at least within some feasible space, that they're not doing something crazy. And then this kernel that's being specified in the Stein variational inference approach actually is the thing that encourages trajectory diversity. So here we add in a trajectory and it would look at all other samples that we're using and then encourage diversity in the trajectories while also converging onto appropriate ergodic coverage patterns. So in practice, what it looks like in practice, this is a uniform coverage problem over some 100 by 100 meter domain where you have a bunch of trees in the way. And these are all the trajectory solutions that we get to uniformly cover and explore this forest domain. So one of the things to note is that actually here on the bottom left, that through this approach, our initial iterations actually first diversifies the ergodic trajectory. So we get actually much more poor loss, but because once the trajectory is spread out enough, we actually go and converge towards almost the same levels of ergodicity as if we were just to do some random sampling and push forward a trajectory through the ergodic metric, which is actually very good, right? That means we do actually see these multiplicity of solutions and we do get some notion of robustness here in the fact that we have many different ways to explore. In fact, you have to do it this way because even if you were to try to randomize those trajectory and then push it through an optimization, so change the initial conditions, you wouldn't get the same diversity as if you were to explicitly optimize for that. So here's sort of all the example trajectories that we're seeing. This is the same optimization, and they all yield very similar levels of ergodicity. The other advantage here is that, in fact, the approach actually has very little computational overhead. And you can actually parallelize that on a GPU. So this is an example right here on the right, where we got a drone, and then we had it try to sample these 4 peaks with all these obstacles, these dynamic obstacles in the mix, where the roller only gets a snapshot of what the obstacles are at every instance. It doesn't know where it's going to go next. And what you're seeing is about 20 coverage patterns or coverage trajectories where the robot's trying to navigate around the object, provide multiple solutions, and then ensure that it takes samples. What you're seeing in the back is the blue of where the robot has been sampling. So this is incredibly fast. So you get about 66 microseconds per iteration of the Stein variational inference. What that means is we can run it on a robot. So this is an example, that same example, but now we have a student here who's holding an obstacle, and what you see on the right is our optimization formulation where this robot is trying to plan around the obstacle, ensuring samples are being collected. And so it's trying to persist in its sampling problem, its coverage problem, irrespective of sort of the external disturbances, which is actually very exciting. We can also use this formulation actually to facilitate sensor-driven exploration. This is sort of that other component that we like. We don't want to be tied down to a specific sensor. In fact, we did this with a sonar-based sensor, and the problem is to collect data in high entropy regions. So what we found is actually the multiple redundant solutions actually provide a lot of robustness in the way the robot explores. The exploration plans that we're optimizing are readily adapted as data is collected. So as you can see, as we get either information map or information measure that we defined changes, we're also adapting our trajectory. And so this is actually quite nice because we do get to sort of apply this to very different problems with different kinds of robots and sensor constraints and information constraints as well as establish the notion of robustness. So that's that. So the last thing we'll talk about is how do we generalize exploration? So we talked about time optimal exploration, we talked about robust exploration. The thing that we care about next is how do we generalize exploration, specifically generalize ergodic exploration. This is work done by my student Christian, collaborator Houston, Derek, and Fabio. So if you noticed, all the problems we've been solving have been on a square and convex domain. That's nice, but robots can go beyond scoring convex. So how do we actually generalize exploration to any arbitrary domain and specifically arbitrary robots? So for instance, I want to do inspection of this bunny. How do I exactly generate points or generate a coverage path that will do that? Something like on the bottom left here. So the way we looked at this problem is we first looked at a general definition of ergodicity. So we realized that, in fact, this is the definition we have in the paper. This is something we actually just got accepted at ICRA. So what we found was that, you don't have to read this, the TLDR says that at all, which is that anything that metrizes weak convergence. So if you could put a metric on a notion of weak convergence, which weak convergence here means that time average statistics as t goes to infinity approaches spatial averages. This is an approach. This will be eventually. This is not a strict convergence. So if anything that can write a metric on this over any compact domain, where one of the distributions is a parameterization of time, the other one is in space, is in fact a proper ergodic metric. The challenge we had was like, okay, well, how do we represent any compact domain? And one of the ideas we had was using what's called a two-sample statistical test as a way to measure distributions. That actually does not require any explicit domain definition. The other approach would be to solve the ergodic metric over some, say, mesh, compute basis function on that mesh, and then solve the ergodic metric that way, which can be a bit computationally expensive. We want to know, can we avoid that? And the way we did it was through something called maximum mean discrepancy or ergodic maximum mean discrepancy. So the idea is that maximum discrepancy is a two-sampled statistical test. So what it does is it compares two distributions through their samples alone, and it tries to embed the samples in a kernel mean embedding. Okay, so we're looking at modes in a Hilbert space. And in fact, that sounds complicated, but in fact, very easy to compute using only samples from their domain and using knowledge of how does my robot project itself onto that search domain. In fact, so it ended up being this really clean sum over samples of your domain. First thing is this first term here is what encourages trajectory diversity. It says, hey, spread out your coverage path. The second term says, well, make sure you at least take some samples that are meaningful on your domain. And the largest just in the last term here is just an offset term. The key thing to note here is that you need IID samples from what you define as information on your domain. We're calling it mu here. However, you don't need that for your time average trajectory statistics because IID samples are only useful if you have to approximate your distribution. We exactly specify the time average trajectory statistics. So we don't need IID samples. We just have it exactly. What that means is when we plug it back into the expression, note that the last term doesn't mean anything. We actually have a very clean definition of this ergodic MMD metric, which we use for optimization. And the key thing here to note is that we don't have to do any special basis functions computation, but instead all we have to do is just change the kernel function. And by changing the kernel function, we ultimately change the domain specification. So turns out this is really fast because it's on samples. You can find on a GPU. Here's some examples where we show first the domain samples. We purposefully offset the domain so we're not in colliding with the bunny. We compare it to a traveling salesperson coverage path, where you have to visit exactly every point. And then our approach, which allows more flexibility but provides that good level of coverage everywhere. We also compare it to a existing method called HEDAC, which uses the diffusion PDE to solve for ergodic trajectories. This is also using some notion of basis functions and solve a PDE. The issue is that with HEDAC, you have to sort of do a one-step look ahead. With our approach, we can look at the trajectory as a whole. So you actually get a full coverage trajectory almost instantly. This is sort of the last couple of bits. We also were able to add in differential kinematic constraints, where now we're exploring this bunny, where the domain is on the bunny, but we're solving the optimization over the joint space. And on the right is doing inspection of a submarine, and we define the problem in the special Euclidean group. Who wants to play? There it is. So this is one way to generalize exploration where we don't actually really, all we need is really samples from the domain, and the domain can be actually very flexible. Okay, so this is sort of towards the end of my talk. So why is this exciting for us in robot learning and what we're doing with it? Well, one of the things that's really exciting about ergodic control, especially for robot learning, is that Your data sets that you want to collect for robotics, well, you want them to be ergodic, right? You want them to cover as much as possible the state distribution. And so one of the things that ergodic control can enable is actually establishing that guarantee that we'll actually provide some diverse and widespreading data set. This is very good for doing things like system ID and learning about dynamics. It's also incredibly useful for scenarios where your rewards or your interactions are very sparse. So if a robot has to go out and seek interactions like contact, our approach is actually very amenable to doing so. And last, what's really exciting is that we can consider now exploration in scenarios where dynamic feasibility is really a concern. So for instance, when you're exploring more dynamic spaces, so like in acceleration or forces, so oftentimes safety and stability can be a concern. We can actually integrate that pretty easily in our approach. And also, if you actually have to consider dynamics in the problem, this approach is actually very useful. So what you're seeing here on the right is sort of a sampling task where you have this double pendulum constraint, and the robot has to be very careful about tipping that over. All right, so this kind of concludes my talk. I'd like to first acknowledge all the students that have been working on these projects and our collaborators and our sponsor. All right, thank you.
Thank you very much, Jan, for the excellent presentation. So yeah, we'll be moderating the Q&A session that is starting now. So you can either like directly unmute your microphone and ask the questions. You can also use the chat window if you wish, and I will read the question. And maybe I will initiate with one. So as you know, Jan, so I like very much like ergodic control, ergodic planning. So it's really to me a topic of research that is really linking like different fields of research. And I also like the fact that it can be used for problems where the duration is given, so more as trajectory optimization, and problems that are maybe closer to control where maybe no duration is given. So I can think of applications here that is more about like the first category could be maybe painting something where we let the robot do it with maybe 10 seconds and we give it explicitly that we have 10 seconds to make this coverage task as efficient as possible. On the other category where no duration is given would be more like maybe a cleaning task where we would like to clean as fast as possible, or maybe a search task. But what I wanted to discuss with you is that the result that you obtain is quite different in one case or the other. So in the first case, we will see like patterns appearing, like it will be a bit more structured, like when you optimize for the full trajectory. And I wanted to see with you, like, is it correct to say that that if the duration is given in advance, so if we optimize for a trajectory, is it similar to a traveling salesman problem, but that would be viewed more in a continuous way because we have like a still, is it correct to say that, or are there like some theoretical background linking the two?
So I'm always hesitant to say that it's a theoretical yes. It is similar. So in a TSP, you want to visit every point at least once. In ergodic control, it's not visit once, right? It is visit proportional to how much time you have left. So in a sense, if you have a space that's defined by, let's say, I don't know, a 100 or a 10 by 10 grid, and you only have a 100 DT or 100 trajectory points, ideally, it would be exactly TSP. I believe we can show this because what will happen is the solution would say, oh, if you have no constraints on your robot, the solution would be put your robot point or your delta function measure on each of these points, right? And then assuming it's uniform coverage, it would be exactly TSP. Now, if you have one extra one or one lower trajectory point, that changes the problem. It will move a little bit. So it is a continuous analogy of TSP. If you have more points, the approach would try to spread out more coverage. I think a TSP is saying, if I have exactly n points, I will give you n trajectory points. In ergodic control, we can be flexible. We can say, I have way more points, spread out the sampling, right? And that's a nice like robustness argument, right? I like to sample more points in more regions, so include more redundancies, right? Because sampling once is not useful, right? You don't just sample once in one place, you sample many times, because noise is going to be a problem. So I would say in the perfectly exact case scenarios where you have exactly the same number of points and you discretize your space, I think they would be exact.
And as a follow-up question. So as a side effect of this, if you give like a distribution to cover that is clearly multimodal, you know, like where you have some areas to explore that are really like disconnected one to the other. So I can imagine that if you know the duration in advance, then what would be optimal is to move only once, to make only one transition from one of this mode to the other mode.
Yeah.
While if you don't know in advance, you will tend to move back and forth because you
A lot,
don't know
yes.
so
Yeah.
so the related question is is there a way in some way to predict with time going on, like how many times we will make these switches between one mode to the other? Maybe, you know, if we know, maybe if we take a toy example, like if we know the distance between the modes, and maybe these modes are very, you know, like we know exactly what they are. Maybe it's Gaussian distribution, or is there a way to know actually how many transitions we will have?
So I don't know off the top of my head how many transitions you would have. That's an interesting problem. I think you can do some 1D experiments where you calculate that in a 1D bimodal case. However, it depends on how you formulate the problem. If you do it the sort of one step receding horizon, one step look ahead. So kind of like Stefan did and everyone else, you have them as well. I don't think there'll be any what I call station keeping, where you stop. Right? You've already gone back and forth a bunch of times. You're like, okay, I explored enough. I think you would continue going back and forth until infinity, because the idea is that you have infinite resolution, right? And so the idea of having infinite or it's infinitely testing small width doesn't make sense. So I don't know if you can actually put a number to it. However, in a scenario where you have either sort of you're forgetting where you've been in the past, or you have a finite trajectory, I believe there is a finite number. I don't know what that number would be, and it would have to depend on your constraint on cost or in control cost, an effort constraint. Then it would change how many times you go back and forth. However, in the multi-agent setting, I know for a fact that you can get something called station keeping, where so you have two robots, two distribution, they will just sit on them, on the two modes. And this will happen eventually. It just takes some time. And this depends on how you've penalized, you know, going from one to the other, or if they can't visit certain areas, or the weight of each robot is different, whether or not they take more measurements there. They will eventually station keep.
No, I see.
So yeah, so I'm not sure if it's a good number. This would be an interesting algebraic exercise to try. I'm sure there is. There must be. I just don't know what it'd be. And it's going to be a bit more complicated because it does depend on your dynamics. I think if you had infinite teleportation, we can maybe make, I think actually that might be a good way to call it out. If we have infinite teleportation, how many times do you go? And I would say it'd be proportional to how many points you have that you're using, so how many trajectory points.
Thanks. So questions?
Also, maybe use a different slide that would get you a bit more excited, like this one.
Yeah. People in my group, I'm sure they will have questions. Like I see,
Oh yeah, I figured.
being connected, James as well. So don't be shy.
Can I
Max.
ask a question?
Yes,
Hey.
please. Hello.
Yes, Max.
Hi. So the ergodic metric itself doesn't really explicitly capture the geometry of the trajectory, in my understandings. And what I mean by the geometry is like things like self-intersection, right? Because there are robotics like having certain number of self-intersections, like in SLAM, there'll be loop closure. That's very important. I previously I did not think we can explicitly address that as part of the trajectory optimization problem, but after thinking more about your like time optimal ergodic control, ergodic search work, I think there might be a chance to just put that as part of the objective. So I wonder if you have any insight on that.
Yeah, we haven't run into a problem that needed to think about self-intersections, at least not yet. What we have thought about was that the problem that we're solving, it's actually much more related to optimal transport. And you can be clever about optimal transport, and so it depends on which one you're using. So if it's like the kernel density flowing ones, you can get a flow that goes from one distribution to the other, and have that not be self-intersecting, because you need to take into account that Jacobian term. And by
Mhm.
definition, you can't have two things intersecting in that scenario, because then
I
you don't have a
see.
one-to-one mapping. So I think you can force it to happen depending on the approach. However, the ones we're doing, which is these sort of two sample statistical test approaches,
Mhm.
are related but not the same thing. They're not optimal transport. They you can form it as an optimal transport problem, but they won't give you the same thing. In that case, we don't, right? We don't have that problem, or we're going to have self-intersections because you're just sampling two distributions. One is just known, one is not known.
I see.
So I don't know how to enforce it here, but I think in the optimal transport version of the problem, you can totally do it.
I see. I see. I see. That at a high level makes sense to me. That sounds
Yeah,
super interesting.
numerically, I have no idea how to do it.
I see.
Like I had to think about it a little bit harder. Yeah, self-intersections are easy. You would also have to think about the trajectory itself and what does it mean to self-intersect. I guess you don't want to visit points.
Because self-intersecting or self-intersection often naturally happens in
Right.
ergodic. But sometimes I just wish I can control that while maintaining the same ergodic,
Mhm.
like the same artistic level, but haven't figured out a way to do that yet. So just
Yeah, so I will say in the time optimal stuff, sometimes we never got self-intersections, but that was by chance.
I see.
Even when we were to get like these like very clean, coverage patterns that looked like a Balserfidon coverage, there would be a scenario where we fed in the optimizer the wrong way, the initial condition, and then we would get a self-intersection in one of the loops. It would go past it and go the other way. So we still get it. Can't avoid it. I would say, yeah, I mean, the thing that's missing really is like these terms that will push you need a term that would look at pathwise the costs between the path direction and where you are currently along that path. So you need some sort of convolution on the path and compare it to everything else in the path.
Yes.
That
That
would be a little bit
convolution
more.
kind of already existed in the maximum mean discrepancy metric, though, right? With the
It kind of does, but not necessarily in the same way. Like you're doing it based off point to point comparison. In a sense that you're right, you are kind of doing it. But that's just for similarity. I don't
I
know. There's
see.
no path dependence, right?
Yeah.
So that's where you run into problem is that, hey, between 2 points, are they related? And the answer is they are. You have to, I mean, what you can do is you can interpolate between them, right? And then compute a continuous version of that. Then I agree, yes, you can. But unfortunately, so long as you have gaps and you discretize, you will always have
Yeah.
that problem. Yeah.
I see.
You
I
can
see.
probably control it via the length parameter. That's one way of doing it. Just like change the length, span it out, and then try to like, fill the gap between. That's maybe one way. But I can always imagine forcing it to happen, or forcing that intersection to happen.
Mm-hmm. That sounds about right.
Yeah.
Yeah, thank you.
Yep.
Hello, I have a question. So thank you for this nice presentation. So like my question is regarding the maximum mean discrepancy. So the ergodic metric that you have here is unlike the ergodic metric which is based on Fourier norm, Fourier series coefficients. There is no special prioritization of low frequency components, right? So do you
Correct.
have a similar behavior where if you have multiple modes with MMD metric, you would also discover these modes
Yeah. So strength
very
is
easily
yes.
or not?
Yes, strength is yes. The thing that saves us is that the MMD metric depends on samples of the space. So the idea is that your samples are coming from whatever measure you've defined in that space. So for example, in this bunny here, what you're seeing is actually we take more samples on the ears and less samples over here. So it just depends on how good you're able to sample. So you can think of the sample as like a depth cloud, or a point cloud. Okay. If you have access to sampling that distribution and you had two modes, you would just get points and say, hey, go to this point and go to this point. Right? And so your MMD metric would include those samples from those two locations.
So on that regard, I understand it would be ergodic. So you would
Yeah.
also like sample the other mode,
Mhm.
but you wouldn't necessarily make the switch initially a bit more like SMC does, because like you would focus more on low frequency components first. You don't have that kind of weighting based on the spectral decomposition.
Correct. Yeah. Because in a sense,
right?
they're all weighted equally. It all depends on frequency, right? The sampling frequency. So like how many samples you get from your space will determine that. So the more you samply dense your space, you might get this behavior, but naturally, yeah, you won't. You won't get that same spectral. Because in a sense, what you're doing with the spectral is you're taking actually the whole space, right? You know the whole space ahead of time and you know the information measure, and you're getting all the high frequency modes. I don't have that. The reason why we wanted to avoid this, we said like, look, I can't have this all the time. I want to generalize this as much as possible. The easiest way to generalize is say, I'm only taking samples, right? So anything that I'm saying I can sample from is okay, or I do lose those spectral behaviors, especially at the higher frequency. I would have to eventually sample almost infinitely and resample to get that kind of behavior. For the most part, it looks very similar. It's the long-term behavior that we lose out on. You also give away the spectral components with respect to the length parameter, right? So the length parameter of the kernel is now what governs how much you explore. So anything below that length parameter, you're in trouble. That being said, we are thinking there's a kind of trick here you can do. You can still recover a spectral decomposition with this approach, is that the choice of kernel matters at this point. So one of the examples would be to rewrite the kernel as a Fourier, a random Fourier features. Then you recover all the spectral components back. But that would be the only way to do it.
But okay, I see. But then I think you would be also kind of like having some kind of basis functions which is specific to that domain.
Exactly.
So,
You would have to figure it out. So you would have to you basically go back and have to do all the work ahead of time. Or what is the domain? What's the basis on that domain? Can I actually write it out because your kernel changes? So the difference is here, I'm only specifying a distance metric on the geodesics, easier to do. Specifying a basis function on the space is harder to do.
okay, thank you very much.
Any other question?
I had a quick question.
Yep, go for it.
So I really enjoyed your presentation. And yeah, I was just curious, you mentioned that this had application for system identification. I was curious for if you knew, or if your group was working on that, or if you know of other groups that are already using it in terms of maybe like dynamic system identification.
Yes. Here's a couple of papers. Really the first two. These did, yes. So sure, yes, you can totally do it for system ID. That's one of the things we did. We said, hey, explore your dynamics. So you see on the top right here is exactly that. We're doing the blue robot is doing ergodic search, and it's doing system ID while ensuring it stays upright. So it's learning in this case, we're doing a neural network model, I believe. And it's kind of perturbing its own explorations, its own state space.
Okay, but and then these are the works from your group then.
Yeah.
But and that's like most of there's not that many other works that are happening yet with that type of thing.
No, not right now.
Cool.
Well, yeah.
Okay.
We have a few more, but
Thanks so much. That's exciting.
Yeah. Thanks.
Okay, any last question for Jan?
Maybe if there's none, I can ask another one. So in Stein ergodic control work that you mentioned, there I couldn't really understand it so good. I need to check the paper, I guess. But like you were considering like also updating target distributions, right? So at some point you were saying like, okay, so you're updating the utility map that you give for that optimization problem, and you were still adapting. Okay.
Yeah.
Because that's
That
also
was...
like something I'm curious with this ergodic control work, because like it feels like with the utility map, and since like this ergodicity is kind of defined when for large times or time goes to infinity, when you keep updating your target distribution, I was thinking about like how, yeah.
So short answer, I can't talk about it right now, but we have some proofs which define now ergodicity for a time, not only a time varying domain, but a time varying information map, but also a time varying domain. So we had to rewrite the ergodic definition, it turns out you can do this. It just requires a bit of finessing and thinking of push forward and push back operators. So what you do is you push everything back into a unifying space, and then you define ergodicity there. It's the same expression. It's just in your optimization, you have to take into account where you have gone and what has been moved, and you invert it back. So your optimization always stays in the same original space, but in fact, what's happening is you're pushing your dynamics and your robot forward. So you can't do it. And there is a reasonable way to do it. It's just you have to think of it in that weird way of like, okay, things are moving, but they don't really move. They're all actually still in the same space, and our optimization stays exactly the same. And then ergodicity still holds.
Okay, so you kind of find a canonical space that you always perform mapping with respect to, and you solve the problem in that space.
Yes, exactly.
Okay.
And then we say anything
Okay.
else is a subset in that space, and then ergodicity is always defined as a subset in that space. It's moving in it.
Okay, sounds great. Thanks.
Yeah, great question though.
Okay, so thanks again for this excellent presentation. It was very, very good to see this new work, and yeah, always fascinating to see what we can
Thank
do
you.
with these ergodicity measures. So yeah, thanks everyone for attending the presentation, and
All
see you
right,
soon.
thanks everyone. All right, bye.
Bye bye.